Hi.
Hey, Alicia. Hey, Annie. How are you?
Good. How are
Hi.
you?
Yeah, I'm doing fine. Did well on my exam I had yesterday, so I'm like less stressed now.
Yay.
It's
So,
good.
do you have anything else to study for, or you're just relaxing now?
Um, I'm relaxing now. I have a quiz tomorrow, like a 20-minute quiz, but that is like based on 30 slides, so I think I could like study that like tonight or tomorrow because it's at like 4 p.m. So then I'll be fine on that quiz. Yeah.
Mm,
Uh-huh. Let's see. So today's office hours, I'm gonna go over these aldol mechanisms for Chem 8B, and then we could go over Chem 118A questions, and then we could alternate between 8B and 118A. Mhm. When's your next? Wait, you only have two midterms, right? For 118A, or three midterms for 118A.
just two, and
Oh,
then
okay.
the final.
I see. So you just have the final now. Like you already took your two midterms, or uh,
Yeah,
okay, that's good. That's good.
but I haven't gotten my results back from a midterm two.
Oh yeah. Do you know what the average was for way for midterm one?
Um, I don't, but what I've heard from a lot of people is like it didn't go so well for Waze.
Oh yeah. Oh yeah. She doesn't release the average. You told me. I remember. Yeah.
Yeah, she
Uh-huh.
doesn't.
Let's see. Okay. So Annie, this right here, what reaction do you think is going to happen? Oh wait, no, they tell you here. It is going to be a base catalyzed condensation reaction, so aldol condensation with these two aldehydes. This aldehyde reacting with some sort of base. So your first step here is correct. We are going to deprotonate the most acidic hydrogen, the alpha hydrogen. So this is the carbonyl carbon here. This is the alpha hydrogen. This is the beta uh, hydrogen or beta carbon, right? So the strong base here, hydroxide ion, is going to grab that alpha hydrogen, form as an enolate ion, which is correct what that you got here, O minus. But our nucleophile here is not this O minus, right? Our nucleophile here is gonna be this alpha carbon because when we draw its resonance structure, when we reform that carbonyl, we could pop this double bond onto that oxygen onto that carbon, giving that carbon a negative charge. So if we draw out the resonance structure here, we see that the negative charge on the carbon is less stable than the negative charge on the oxygen, right? Because oxygen is more electronegative than carbon is, so oxygen is better able to hold that negative charge, whereas carbon is less electronegative than negative than oxygen, so carbon is not able to hold the negative charge as well as oxygen. And because this is less stable, it is going to be more reactive, more nucleophilic. So we're going to bring in our second equivalent of aldehyde here, where I'm gonna star my nucleophile, which is that carbon right there, and I'm gonna dot my electrophile, which is that carbonyl carbon right there. So,
Wait,
yep,
when I
uh-huh.
draw this reaction, do I have to put the brackets around the resonance forms or is it part of their mechanism?
Yeah. So the brackets represent resonance structures. You do have to draw a double-headed arrow here because these are the same structures, just resonance structures of each other. Um,
Oh, okay.
Felix, he doesn't really put the brackets for resonance structures, but
Mm-hmm.
it's more accurate to put brackets to show that they are resonance structures, but he doesn't really
Okay.
care. Yeah.
Okay.
Yeah. Mhm. Right. So this alpha carbon here is our nucleophile. This carbonyl carbon of the other aldehyde is going to be our electrophile. So what's going to happen is that we're going to have that nucleophile attack that electrophile, but that's going to break the octet rule for this carbon because this carbon here already has 4 bonds. 1, 2, 3, 4. We're trying to make another bond between the star and dot carbon, but that's going to be 5 bonds. So to conserve the octet rule, we have to pop this double bond onto the oxygen. And when we do that, we're going to create this intermediate here. And the way that I'm going to draw this is like this. So I'm going to draw my aldehyde of the star carbon like that, where this is the star carbon. We see that this star carbon here is attached to a methyl group, which is this methyl group right here. I'm going to shift that methyl group going down. And the reason why I did that is because I want to make the new bond between the star and dot carbon in a zigzag bond line form, right? So this is the star carbon, this is the dot carbon, this is the new bond between the star and dot carbon, right? That new bond was formed from this arrow, from that attack. Then we draw what is attached to the dot carbon. This dot carbon here is attached to an ethyl group. We see that ethyl group right here. A hydrogen, but I'm going to leave that hydrogen as invisible, which is this hydrogen right here. And it used to be double bonded to an oxygen, but now it's single bonded to an O minus when we pop that double bond onto the oxygen right there, right? So looking at your structure here, this is the starred carbon, this is the dot carbon, this is the starred carbon, this is the dot carbon, right? This dot carbon here is attached to hydrogen, which is that hydrogen, an ethyl group, which is an ethyl group, and a single bond O minus. So the carbonyl will not be there. We need a single bond O minus on the dot carbon.
Oh, okay, got it. Yeah, that
Right.
part really confuses me how to add them together.
Yeah, connecting the pieces together, right?
Mhm.
But does the star and dot technique like keep track of everything for you? Like, does it help keep track of everything? Yeah.
Yeah.
Right. So now once we have this right here, the next step is to protonate the O minus with our product solvent, which is going to be water, to get our neutral alcohol. And this product that we get here, when we have an aldehyde, and beta to the aldehyde is an alcohol, right? So this is the aldol addition product, right? And this is what we call an aldol. The aldehyde part is there, the O part is here, aldol, aldehyde, alcohol. The alcohol has to be beta to the aldehyde. It can't be alpha to the aldehyde. That's too close. It can be gamma. That's too far. It has to be beta to the carbonyl to be considered an aldol. Aldol. But that's the aldol addition product. He might want you to go all the way through to the aldol condensation product, right? So we won't stop here if we do aldol condensation. To do aldol condensation, what we have to do is bring in another equivalent of base, deprotonate the alpha hydrogen in between the carbonyl and alcohol, generate the enolate ion, right? Our goal here is to get rid of the alcohol, right? Get rid of this alcohol and put a double bond between the alpha and beta carbon right there to get the enone or alpha beta unsaturated carbonyl. So once we have this enolate here, an alkene next to this O minus, we're going to reform that carbonyl, shift the double bond over to make a double bond here, and then kick out the OH, which is going to give us well, this product here, which we see that if this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon, we see that there's a double bond between the alpha and beta carbon, or an unsaturation between the alpha and beta carbon. So this is what we call the alpha beta unsaturated, because there's an unsaturation between the alpha and beta carbon, carbonyl, right? So alpha and beta to the carbonyl, there's an unsaturation between them, a double bond between them. And this is the aldol condensation product. Aldol condensation product.
Are these not reversible steps?
Oh, these are reversible steps. So we would put reversible arrows here.
Okay, got it.
Yeah. The only irreversible step would be, I would say the last step here, when we kick out the OH minus. Right? But everything else would be reversible.
Okay.
And the reason why the last step is like irreversible is because we're kicking out that OH minus group, which is like a not very good leaving group. But the reason why it's able to leave is because we have heat, right? So when we have heat, aldol condensation is going to happen. But if there's no heat, then aldol addition is going to happen. You stop at the aldol addition.
So at which arrow do we and we can assume water is already there? Oh, okay, I see.
Yeah. We assume water is already here because we used OH minus as a base. If we were to use let's say OCH3 minus as a base, our proton source is going to be methanol, like the protonated version of the base we use. The base we use was OH minus. The protonated version of OH minus is water, H2O.
Okay, that makes sense.
Yeah. Okay. Next one right here. Let's see. So this is going to be very similar to the previous example. This previous example is an example of a self aldol. if you have heat, aldol condensation. If you have no heat, aldol addition. So I'm just gonna say self-aldol reaction, right? But most likely they want you to do condensation, aldol condensation. This one right here is gonna be a crossed or mixed aldol reaction.
Okay.
Right. So we have acetone here. Oh wait, no. Let's see. Let me see this here. CH3, CO, CH3. Right. So you drew out an aldehyde. Be careful. An aldehyde would be that would be like CH3 CH3 basically. Right. There's some CH3 here, and the CHO is the aldehyde. But we have a ketone. Right. This is going to look like this, where we have CH3 at the left side. The CO is the carbonyl, and then the other CH3 is the other CH3 right there. Right. So that's the acetone. And we have 2 benzaldehydes. That's good. So, oh wait, yeah. So you got the right enolate structure, right? But then you uh, we want to draw a bond right there between the carbon and hydrogen, because that looks like an aldehyde. Right. So that case, the very enolate ion, star that, dot that. That's the correct mechanism. This is gonna be, let's say, the star, the dot. Yep, you connected it correctly this time. This is the new bond between them. That dot is attached to a benzene, which is this benzene, a hydrogen, which is invisible here, and it was double bonded to a oxygen, but we popped that double bond onto the oxygen to create that single bond O minus right there. So this is the correct connection here. Now, once we have that, we protonate the O minus with water to make it neutral. And then this is the aldol addition product. We stop here with no heat. But if we have heat, which we most likely will have heat, we do aldol condensation, which is to deprotonate the alpha hydrogen in between the carbonyl and alcohol, generate the enolate ion. And then once we have the enolate ion, it does like a boomerang kind of step. It goes back to reform the carbonyl, push the double bond over there, kick out the OH to create this enone here, or alpha beta unsaturated carbonyl, right? And let's see here. Yep, generate the enolate ion here. This one here. That's another aldol reaction. Star dot star dot. New bond between star and dot. Dot is attached to O minus benzene. Protonate to become OH. Aldol addition product. And don't forget the double bond right here. Right, the double bond is not here. Double bond is right there between the alpha and beta carbon to the carbonyl. Right. Now, once we have the aldol addition product, we do aldol condensation by generating the enolate ion. Once we have the enolate ion, we do the boomerang step to reform the carbonyl, shift the double bond over, and kick out the OH to create. Oh yeah, so what you did was that you put the double bond onto that carbon, giving that carbon a negative charge, and then that negative charge goes to that double bond right there to kick out the OH. But we could do it in all at one step by just reforming the carbonyl, shifting the double bond over to make a double bond there, and kicking out the OH to go straight to here. Right. And if you were to do it this way, then you would have to draw these arrows here, the double-headed arrows, to show that these are resonance structures of each other. Right. But you could go straight from here to here, just by making the carbonyl, shifting the double bond over, and kicking out the OH at the same time to create that structure there. Yeah.
Wait, why would the double bond be not where I originally put it and where you put it?
Oh, let's see here. For this one here?
Yeah, why is it not?
Yeah, because where you put it right here, this carbon breaks octet row. 1, 2, 3, 4, 5. And also, if you look at the mechanism right here, you put the double bond right here, right? Which is this double bond right here.
Oh, wait, I got confused with the other bond. Oh my gosh, there's so many things going on.
Yeah,
okay, yeah, I get it now. That was no, never mind. I get it.
Yeah, you put it like right here instead.
Yeah.
Right.
Okay, that makes sense.
Yeah.
Okay, awesome.
Yeah. Next one. Wait,
Wait,
is it?
no, they're all the same thing.
Okay.
I just
So,
kept sending you my different tries.
oh, you different try. Oh, yeah, this was your final answer, right? Like this is the final answer you tried. Oh, I
No, I
tried
got
that
it
small
wrong though.
penis. Oh yeah. So what's the problem here? Can you find the problem in this mechanism?
Let me see. I think I attached it wrong.
Right. So you
Like
did correct
there's a
star dot.
hydrogen instead of a methyl.
Yeah. This dot here does have a hydrogen. It has an ethyl, which is this ethyl, but no more single double bond O. It's supposed to have a single bond O minus. Like there's no double bond O
Mhm.
on that carbon right there.
Yeah.
Right. Uh-huh.
Yeah, that's
Yeah. Hmm.
okay.
Yeah.
Thank you.
Yeah, no problem. Hmm.
Thank you.
Yeah. Hmm. Okay. Hey, Elysia.
Hi.
Let's see. What are you learning so far in 118A?
Alcohols. Wei just
Alcohols.
introduced that, so
Uh-huh.
um, it's a bit confusing.
Yeah.
I mean, I think it's similar, but like
Mm-hmm.
I learned that alcohols they can
Yeah.
act as acids or bases,
Yep.
and
Amphoteric.
then I think we're also in discussions. It's so weird how it's structured, where we have to learn like different sets of material for discussions, and then different sets of material for like the lecture. So
Oh.
we also went into what's it called? Like where we have to use like the idea is we go from like one reaction and we go into a completely different one. And I think that's called
Synthesis.
yeah, synthesis. It's kind of confusing to me cuz I wouldn't really know how to
Like know the reactions required to transform the reactant molecule to the product,
yeah.
like the product molecule. Um, there's different ways to think about it. There's strategies. The best strategy that I use is retrosynthesis, which is going backwards, and then going forward a little bit, and then try to meeting in the middle. So,
Yeah, that's what my TA suggested too.
uh-huh, yeah. Wait, who's your TA? I know them. Like,
Abai.
bye. Oh no. So yeah. I don't know him. I don't know him. Uh-huh.
Okay.
Uh-huh.
Yeah, I input my
Uh-huh.
lecture notes
Yeah.
into the drive. So
Okay.
it's labeled alcohols.
Alcohols. Okay, yeah. Let me import that to the document, scan through it, and then I'll teach you the reactions, and we could try some synthesis rounds together.
Okay, thank you so much.
Yeah. Let's see, discussion slides, no, class resources, um, lecture notes, no, um, lecture notes here. Yeah. Okay. Elimination applications. Application of substitutions and synthesis. Okay. Oh yeah. Outcome lecture notes alcohols. Right here. I see it. Yes. Oh yeah, and you sent it to a PDF format. Yay!
Yeah, I did.
See, send a copy. Notability. Add to note. Import.
I think I understand the nomenclature.
Mm-hmm.
So I think that's not too bad, but I think just like the
Yeah, my nomenclature is so rusty. Like I barely reveal nomenclature rules now. But like it's just a lot of rules and like practice with it, right? Like knowing the nomenclature of functional groups.
yeah.
Yeah. And like finding out the longest chain and stuff like that. Acidity of alcohol. Are these waste notes like her lecture notes here?
Well, those are like my written notes, but
Oh wow. Yeah.
that's like her
Like
like
blank
that's
copy.
her, yeah, her yeah, through her blank
Yeah.
copy.
Uh-huh. And then you annotated. I see. That's so good. Okay. Okay. Wait, what? Okay. Let me read through this notes and let's see what is tested here. Let me make notes in red. Nomenclature. Acidity of alcohols decreases with longer alkyl chain. pKa goes up as you go up. No bulky base. Up. Yes. Okay. Water. methyl hydroxides can deprotonate, or metal hydroxides can deprotonate alcohols to generate alkoxides. Alkoxides are the O minuses. Acidity of them, methanol, primary, secondary, tertiary alcohol. Tertiary is the weakest acid. Yes, that makes sense. Induction effect on alcohols, acidity, resonance 118B, pKa goes down. Induction effect, okay, yep. Basicity of alcohols, lone phase electrolysis make alcohols weakly basic, can both, yep. Amphoteric, okay, yes. Uh, Nucleic acid, pKa of this one here, yeah. Stronger acid, yep. Exposed more. O minus exposed less. Nearby electronegative groups on the alkyl chain increases the alcohol's acidity. Okay, yep. Exposed more, yep. Approach synthesis of alcohols. Okay, so this right here, SN2. This one here, SN1. This one here, SN1 E1. Approach 2. Prevent the competition with elimination reaction. Oh, ester hydrolysis. This is okay. So this ester hydrolysis here, is introduced in 118A
Mm-hmm.
as a reaction, but the mechanism is a 118C
Yeah,
mechanism,
that's
chapter
what
20.
I stated. So, like
Uh-huh.
even the what I wrote in the lighter blue, she
Uh-huh.
said that that's not really like entirely focused. It's just like the
The
idea,
reaction,
the
yeah,
react.
like
Yeah.
mhm. Right. And the way that you can think about it is that when you identify your ester group here, and then you react it with NaOH water and acid NaOH water, you're gonna convert that ester into this alcohol right here, right? Where this carbon here that was holding the ester is that carbon right there holding the alcohol, right? So we're basically substituting the whole ester functional group into the alcohol functional group when you see these reagents here. Yeah, right.
Okay.
And that is ester hydrolysis. We're hydrolyzing the ester into the alcohol, and the other thing is going to be carboxylic acids, but we're not going to worry about that for now until 118C. 118C. Uh-huh. Right. Reactions of alcohols. Okay, so these are the oxidation reactions. PCC, fast reaction learned in 118B, chapter 17, hemiacetal. Oh, no, this is geminodiol, Jones, secondary alcohols. Okay, yeah. So this whole oxidation reduction thing here, there's a chart that I want to show you that will organize all these reactions very clearly in all in one table.
Okay.
Right, PCC. Okay. Let's get started with the acidity of alcohols. Okay. So um, I'm gonna give you different molecules here. The first molecule is gonna be water, H2O. I'm gonna give you methanol, CH3OH. I'm gonna give you some sort of primary alcohol, some sort of secondary alcohol, and some sort of tertiary alcohol. Right. So water here is not an alcohol. It is H2O. But all these other groups here are alcohols. Right. ROH, ROH, ROH. And I'm gonna explicitly draw out the bond between the oxygen and hydrogen, like this. Right. And we're gonna look at the acidity of these hydrogens here underlined in red. So let's say that some kind of base comes in and deprotonates all of these oxygens by grabbing the hydrogen, and the bond between the hydrogen being grabbed and oxygen, those two electrons are gonna go onto the oxygen right there, like that. Right. And I'm gonna draw out the conjugate bases in blue. We're just gonna take away the hydrogen on the oxygen and give that oxygen a negative charge. Right. And these right here are the conjugate bases. When we deprotonate the acid, we get the conjugate bases. right? And the stronger acid here will lead to a weaker conjugate base from Gen Chem. I think if you remember that concept, like strong acid leads to weak conjugate base.
Yeah.
Yeah, right. And the way that I think about it instead is like this. It's still the same thing, but the way that I think about it is uh, strong acid leads to a stable conjugate base. And I'm going to abbreviate conjugate base as CB. If a conjugate base is more stable, that means it is going to be less reactive because it's stable, it's at peace, it doesn't want to react. And if it's less reactive, that means that it is a weaker conjugate base, right? So that's the same thing. Strong acid leads to a weak conjugate base, but to make it more direct, strong acid leads to a more stable conjugate base. And there's different factors to look at the stability of the conjugate base, which you could use Choreo to determine the stability of the conjugate base, where C stands for charge, A stands for atom size, R stands for resonance, I stands for induction, O stands for orbital or hybridization. Right. So in this case here, when we determine the stability of these conjugate bases, the factor that we're going to look at is going to be a not charge because they all have the same charge. They all have a negative charge. So we can ignore that factor. Not atom size because they're all on the same atom. Oxygen, 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 oxygen. So we can ignore that atom size factor. Not resonance because none of these negative charges can do resonance. So we can ignore that factor. Then we look at induction, right? Where if you see some kind of hydrocarbon chain, like an R group, like this right here, that right there, that right there, think of an R group. This is the key, important takeaway here. R groups are electron donating groups by induction. And I'll show you what that means. Donating groups, EDG, electron donating group by induction. Right. So these R groups here attached to the O minus are inductively donating electrons to the oxygen here, right? So the tertiary alkoxide ion has the most amount of R groups, donating more electrons onto the O minus. The secondary alkoxide ion has two R groups that are donating electrons into that. The primary alkoxide ion only has one R group. The methyl group, methyl oxide, only has like one R group right there as well. And then this hydroxide ion right here has no R groups at all. Right. So we see that there's a lot of negative charges going towards that negative charge. And would that make it more or less stable if negative charges are getting close to each other? Will they attract or repel?
Repel.
Yep, they would repel. So that would make this the least stable conjugate base right here. And that would make this the most stable conjugate base. Right. So we could make a ranking system here where going from right to left is going to be the stability of conjugate base. But going from left to right is going to be the strength of conjugate base. Because you can think of stability as let's say no, stability as stability, but strength of conjugate base as reactivity as conjugate base. Right. Because the most stable conjugate base here, this hydroxide ion, is the least reactive, making it the weakest conjugate base. Right. So if that's the weakest conjugate base, looking at the original acids right here, how would you expect the pKa ranking system to go? Would it increase from left to right or right to left? Or another way you can think about it is which one of the molecules here, like right or left, will have the lowest pKa?
Um, I kind of forgot what we mean by pK. That's acidity, right?
Yeah, acidity. The lower the pKa value, the more acidic the molecule is. So first, which molecule do you think is the most acidic molecule? Comparing these here.
I think, would it be the one on the very right?
Yeah, the one on the very right, this one right here, butanol. Oh wait, no, butanol or turbotoxy. Butanol. This alcohol on this turbotoxy group, turbutyl group, is going to give us this conjugate base right here, right?
Yeah.
And we said this conjugate base is the least stable conjugate base because there's a lot of R groups donating electrons onto the oxygen minus, right? So that's very unstable, right? And if it's very unstable, would that make it more or less reactive? If it's unstable, more or less reactive?
Wouldn't it make it more reactive?
Yep, more reactive, and that would make it a stronger conjugate base, right? So if this is a strong conjugate base, that means that this is a weaker acid.
Oh, so low pKa?
High pKa,
Oh, high pKa.
right? pKa. So if you want to think about in terms of acidity, acidity will increase from right to left. So the most acidic molecule, acidity, is this water here. But if you think about it in terms of pKa, it's the opposite, right? So pKa will increase from left to right, where the lowest pKa molecule is the most acidic molecule. So they're inversely related. The lower the pKa, the more acidic the molecule is.
Okay, so um, what we consider more stable is more acidic?
More stable conjugate base, yes.
More
The more
stable.
stable conjugate base makes the more acidic, comes from the more acidic molecule.
Okay,
Yeah. The less stable conjugate base comes from the less acidic molecule. Yeah.
okay, that makes
Mhm.
sense.
Right. Right. And then also keep in mind of like the inverse relationship between acidity and pKa, because on the test she might ask you about pKa, and then if you think this is the most acidic molecule, which it is, you might like correlate that with the highest pKa, but that's wrong. Right. The more acidic the molecule is, the lower the pKa is.
Wait, can you repeat that one more time, please?
Yeah. Uh-huh. Right. So we know that this is the most acidic molecule, and why is this the most acidic molecule here?
Because it's more stable.
It gives the more stable conjugate base.
Yeah,
Gives the more stable conjugate base. And if it's a more stable conjugate base, is it a weak or strong conjugate base? Is it reactive or unreactive conjugate base?
it's unreactive.
Yep, unreactive, weak conjugate base. So that's why this is the most acidic molecule here. And if this is the most acidic molecule here, would this molecule have the lowest or highest pKa?
Um, lowest.
Yep, lowest pKa. Right. So what I was saying is that if you think of the most acidic molecule, don't say that it has the highest pKa. Wait, say that it has the lowest pKa.
Okay,
Yeah. Mhm.
but
Okay.
that's different from acidity.
pKa is, you could think of it as acidity, where the lower pKa is, the more acidic the molecule is.
Yeah,
Right. The pKa is referring to the hydrogens here. Like you'll see like this, it's like some number, but it would be a lower number than this number here, right? Because this hydrogen is more acidic than this hydrogen over here,
okay.
right? So an example problem would look something like this. If you have this list of molecules, they might want you to rank them in order of acidity. So let's say we have that is that and this and this, right? So if I give you this right here, um, and I want you to rank it in order of increasing acidity, where one is the most acidic and 5 is the least acidic. how would you do this here?
Um, well, we talked about um, the like let's start with the turbutyl. When
Yep.
it has like three things going towards the O, let's say if the hydrogen um, like it leaves and then it gives it a negative charge.
Yep. So that's the first thing. We deprotonate these acids to form the conjugate base to compare the stability of. So let's say all of these hydrogens leave to give the negative charge on the oxygen, giving us these conjugate bases here, right?
Right.
Mhm.
So after that we consider like you said cario. So
Uh-huh.
charge they're all the same.
Yep.
Size they're all on the um, oxygen. Resonance no. And then
Mhm.
so we look at induction where we look at the R groups that are uh, electron donating.
Mhm.
So we know that the tert-butyl, that one is probably going to be the least acidic
Mhm. Mhm.
because there's more negative charges going towards each other and it'll want to
Mhm.
repel.
Yep. Yep. More negative charges, more R groups near it, making the negative charges repel. That's nice. Yep.
Yeah. And then I think that the one that is going to be fourth is the one on the very left.
Mm-hmm.
And then there's um, two negative charges that are going to go towards um, it goes towards the oxygen, right?
Mm-hmm. Yeah, it goes towards the oxygen. Right. Right.
Okay.
Yep.
So that would be this um second least acidic or like
Mm-hmm. Mm-hmm.
fourth.
Yep.
Um, and then I think that the OH, the one right beside
Mm-hmm.
it, that one would be um oh wait, the one between 4 and 5, I want
Mm.
that's one.
Mm-hmm. Oh, this is one right here, the most acidic one.
I think so.
Yeah. So this one here has one R group. There is a molecule that has no R groups that are not donating any electrons at
Yeah,
all. Right. And that is going to be this one right here.
the H2O.
The OH2O, yes. Because if you make
Oh,
the conjugate base right here, there's no R groups on the O minus. It's
oh,
only hydrogen. Right. So there's no electrons going towards the oxygen at all. Whereas this one in the middle between 4 and 5, there is an R group donating electrons into
right.
the O minus.
That's the carbon, right?
Yeah, this carbon right here. Right.
Oh, okay,
Donating electrons.
okay,
Right. So our one here would be this one here, where this oxygen minus has no R groups at all.
right.
Mhm.
So when you were looking at that one, it's H2O, but why did you put it in quotations?
Oh, I put it in quotations to show that this is the conjugate base of H2O. So when we use some kind of base to come and grab the hydrogen of the H2O, that bond between the H being grabbed and oxygen is going to go onto the oxygen, giving that oxygen an extra pair of electrons and resulting in this conjugate base here, the OH minus.
Oh, okay.
Right. So we're just comparing this OH minus with all these other O minuses here.
Mm,
Right, because when we determine the stability of conjugate bases, we look at the conjugate bases.
right.
Mhm. Yeah.
Okay.
Uh-huh.
Um, I want to say the one that I did guess would be second.
Hmm.
I wouldn't be able to reason why.
Uh-huh.
Yeah, those two, like what makes those two
Yeah.
different.
Uh-huh.
I think it's just that that one looks like it has less going towards it versus the methyl.
Uh-huh. Yeah. So it looks less because it's smaller, right? But this is because it's drawn in bond line form. If we
Right.
were to draw in condensed formula, it would look like this, right? And then there's more R groups here on the O minus than this right here on the H2O minus.
That makes sense because
Uh-huh.
you would think would would it make sense to say that the methyl's like more stable?
Yeah, you could say it's more stable conjugate base because the methyl group here is a smaller R group than the ethyl group here, right?
Okay.
And
Yeah.
because it's a smaller R group, it does not donate electrons into the O minus as much, so it would make it more stable, making that number this number 2 right here and this number 3.
Right. So is there a better way to visualize um like the induction effect for this for 3?
Yeah, for three, the better way to visualize the induction effect for three would be, let's say we are comparing um this CH3 CH2O minus would probably be like in condensed formula, and this CH3O minus here. Because the CH3 is a smaller R group, it will donate electrons weakly like that. And because the CH3 CH2 is a bigger R group, it's gonna donate electrons more strongly like that,
Oh,
right?
that
And then
it's
that's gonna repel that negative charge even more than this right here.
you said it's going to transfer more strongly.
It's going to donate electrons more
Okay.
strongly. Donate, yeah.
Okay.
This is donating electrons more strongly than the smaller R group.
Okay, that makes sense. Thank you.
Yep. Yeah. So let's see here. We'll do the PCC Jones oxidation reagent table that I wanted to show you
Yeah.
here. And then I'll see if Wiley or Annie has any other question, but I want to show you this table here for alcohols. Yep. So oxidation and reduction, they are opposite reactions, right? On Way's lecture notes, she didn't go over the reducing agent or reducing reduction reactions yet, but what I'm gonna define what oxidation is and reduction first, and then show you the oxidation table. And then when she goes over reduction, I will go over the reduction part with you later, right? So, and back in Gen Chem, what do you know about oxidation and reduction? If it's okay if you forgot.
I think of oil rig. So
uh-huh.
um I think is oxidation gain and reduction is loss of electrons.
Yep. Oxidation is gain of electrons. Reduction is loss of electrons. Oh wait.
Uh
Oil rig. Other way around. Other way around.
oh. Okay. Oh yeah. Oh wait. Oh yeah.
The other way around. Oh shoot. Okay.
Oops.
I know it's okay. It's okay. The name is kind of misleading because you think of reduction as like losing something. So it looks like it's losing electrons, but it's actually gaining electrons. And the way you can think about it is that if it's gaining electrons, is it gonna gain positive charge or lose positive charge?
Um gain.
If it gains electrons, what charge does an electron have naturally? Negative or positive?
A positive.
Electrons would negatively charged.
Oh
Electrons
yeah.
negatively charged.
Yeah.
Right. And if something is gaining more negative charge, what happens to the positive charge? Does it get bigger or smaller if something is gaining more negative charge?
The positive would be smaller.
Yep, the positive charge should be smaller. So you can think about it as like reducing the positive charge, but um, the best way to think about it is gain of electrons for reduction, loss of electrons for oxidation.
Yeah. And then I think in discussions we only like briefly stated that like in like alcohol chemistry,
Yep.
oxidation is making more bonds to
Uh-huh.
oxygen and reduction is like um making
Um,
more
lo-
bonds to
two
hydrogen.
hydrogens. Yeah. So that was the other thing I was gonna talk about. In Gen Chem, oxidation is the loss of electrons, reduction is the gain of electrons. But in organic chemistry, organic oxidation is the gain of bonds to electronegative atoms like oxygen, nitrogen, or fluorine. When you first learn about oxidation reactions, think of oxygen. Like that's the first electronegative atom you learn about for oxidation. Gain of bonds to electronegative atoms like oxygen. I'm just gonna put parentheses there of oxygen. And then reduction is the loss. Reduce bonds, loss of bonds to electronegative atoms. Bonds to electronegative atoms like oxygen. But if um, something gains a bond, they have to lose a bond to conserve the oxide rule. In oxidation, if you gain a bond to an electronegative atom, you get a loss of bonds to hydrogen. Loss of bonds to hydrogen. In reduction, if you lose bonds to electronegative atom, you're going to gain bonds to hydrogens. gain of bonds to hydrogen, like that. Right. So these are the three definitions that you can keep in mind when you think of oxidation and reduction. Oxidation, loss of electrons, gain of bonds to electronegative atoms, or loss of bonds to hydrogens. Reduction, gain of electrons, or loss of bonds to electronegative atom, or gain of bonds to hydrogen. But in OChem, think of these two more, right? Like the gain of bonds to electronegative atom, or loss of bonds to electronegative atom, or loss of bonds to hydrogen, or gain of bonds to hydrogen. Like these are the more common uh, definitions we use in OChem for oxidation and reduction.
Okay.
Right. So I'm gonna show you different molecules here, where it's gonna be from the most reduced to the most oxidized. It's gonna be a spectrum here. The most reduced is gonna be some alkane, like let's say methane, right? And then the most oxidized is gonna be something like carbon dioxide, CO2, right? Because if you look at the carbon right there, this carbon right here on the left is the most reduced because it has the most amount of hydrogens and the least amount of oxygens. The one on the right, carbon dioxide, is the most oxidized because it has the most bonds to oxygen, 4 bonds to oxygen, and no bonds to hydrogen, right? So if you want to make a chart here, you could say the oxidation increases from left to right. Look, you could say oxidized state, the oxidized state. Oxidized state increases from left to right, where CO2 is the most oxidized, CH4 is the least oxidized. And then you could say that it increases from right to left in the reduced state. So the most reduced state is the methane or the alkane. And then the least reduced state is the carbon dioxide. They're opposite to each other, oxidized state and reduced state. Right. So that the next thing we could look out for is, let's say, make this methanol. So we lose 1 bond to hydrogen and we gain a bond to oxygen. So that's more oxidized than the methane, you could say. So we're going to increase oxidation here. Right. And then we could say now, if we get rid of another bond to hydrogen and we gain a bond to oxygen, we're going to have a double bond to oxygen like that and 2 bonds to hydrogen like that, right? And now that's more oxidized than the alcohol before because this carbon here has 2 bonds to oxygen, making it more oxidized than this carbon with only 1 bond to oxygen. The more oxidized form of that would be if we convert one of the hydrogens to an OH, where we lose that bond to hydrogen and we gain a bond to oxygen.
Okay.
Right. So oxidation, gain of bonds to oxygens, reduction, loss of bonds to oxygen, right? Or gain of bonds to hydrogen. Yeah. Okay. So that's the difference between oxidation and reduction. Now let's go over alcohols. In alcohols, I want you to know what a primary alcohol is, what a secondary alcohol is, and what a tertiary alcohol is. So a primary alcohol is when we have an alcohol bonded to a carbon that is bonded to only one other carbon. Right. So if we have this alcohol here, this is the carbon that we're looking at. That's primary because it's only bonded to one other carbon right there. Right. For secondary alcohol, if we look at the carbon attached to the alcohol here, this carbon is attached to 2 other carbons. So that's a secondary alcohol. For tertiary alcohol, if we look at the carbon here holding the alcohol, this carbon here is attached to 3 other carbons, making it tertiary alcohol. Right. Okay. So now once we know that, and we want to oxidize these alcohols, we have to use something called an oxidizing agent. Right? An agent is a molecule or a reagent that will make a reactant do something. So oxidizing agents would oxidize molecules. And in organic chemistry, when you learn about alcohols, there's 2 types of oxidizing agents. Oxidizing agents. There's a weak one and a strong one. Oxidizing agents. So a weak oxidizing agent that you will first learn is PCC. And you might see that with a solvent like CH2CO2. That's just a solvent. A strong oxidizing agent is going to be Jones reagent. Jones reagent. And there's different forms of Jones reagent that you could see. Right. Think of it as a lot of chromium and oxygen reagents. You could see Na2Cr2O7 H2SO4 and water. You could see CrO3 H2SO4 and water. Right, where the most important indicator here is when you see chromium and a lot of oxygens. Chromium and a lot of oxygens. Right, those lot of oxygens there make it a strong oxidizing agent, right? Because oxidation is the gain of bonds to oxygen or electronegative atoms. So if you see chromium and a lot of oxygens, we associate that with Jones reagent, which is a strong oxidizing agent, right? Okay. Now, once we know the key players for oxidation for alcohols, let's now introduce you to this oxidation table. Right, so this is going to be the type of alcohol on the first column. Primary alcohol, let's say something like this. Secondary alcohol, let's say something like this. Tertiary alcohol, let's say something like this. Okay, and then let's say that we are going to react this with the different oxidizing agents, PCC and Jones. Okay, the first column here, let's say we reacted with PCC and its solvent CH2CO2, or the other one, Jones. So I'm gonna make a note here. This is the weak oxidizing agent. This is the strong oxidizing agent. Okay, the hardest row here is gonna be the primary alcohol, right? Because I'm gonna look at the oxidation state of these carbons here holding the alcohol, which is gonna be color-coded in green. And it might help if you see the hydrogens as well. So I'm gonna draw out the hydrogens in blue. Hydrogen, hydrogen, one hydrogen, and no hydrogens at the tertiary carbon. If we oxidize a primary alcohol with PCC, a weak oxidizing agent, what we're going to get is an aldehyde, where the green carbon that was holding the alcohol is this green carbon right here, right? Where I'm going to make this hydrogen here blue just to keep track of the hydrogens, but this is an aldehyde, right? Where if you look at the green carbon here, it lost a bond to hydrogen to gain a bond to oxygen, right? Before, this green carbon here only had one bond to oxygen. But when we oxidized it with PCC, a weak oxidizing agent, we made that green carbon gain another bond to oxygen, which now has two bonds. But when we gained that bond to oxygen, we lost a bond to hydrogen, right? Before, that green carbon had two bonds to hydrogens, but now it only has one bond to hydrogen, like that. If we use a stronger oxidizing agent like Jones, we're going to oxidize a primary alcohol all the way into a carboxylic acid like this. Because if you track the green carbon that was holding the alcohol, which is this green carbon here, we got rid of all the hydrogens to gain two bonds to oxygen, right? Before, this primary alcohol only had one bond to oxygen, but now it has 1, 2, 3 bonds to oxygen, right? And this is the most oxidized state that, well, no, the most oxidized state is carbon dioxide, but if we use Jones, we're going to oxidize the primary alcohol into the carboxylic acid, which is the more oxidized form than the aldehyde, right? Because the carboxylic acid has 3 bonds to oxygen, whereas the aldehyde only has 2 bonds to oxygen. So that's the difference between using a weak oxidizing agent, which only goes to the aldehyde for primary alcohol, and using a Jones strong oxidizing agent, which goes all the way to a carboxylic acid. Did that make sense, Alicia?
So just to clarify,
Mhm.
so because like let's say for the weak oxidizing, is you said oxidizing agent,
The oxidizing agent, right?
right?
PCC.
So it's not gonna fully like um Is can we say it's not gonna fully react versus like Jones? It will like
Yeah, like it doesn't fully oxidize all the way to the carboxylic acid, whereas Jones, it will fully oxidize or react to go all the way to the most oxidized state it can go to, which is the carboxylic acid for the primary alcohol. You could think of it like that,
so
right?
because the weak one doesn't fully oxidize, what does it do?
Yeah, it will partially oxidize to the aldehyde for primary alcohol. Okay, so
Okay.
this is the primary alcohol here. We're gonna partially oxidize it because we're still oxidizing the primary alcohol because we're gaining a bond to oxygen here. Right before it only has one bond to oxygen, but now it has two bonds to oxygen. So that's still oxidation right there. But it's not as strong as Jones because you notice how we gained two more bonds to oxygen here to why we use Jones. That's why Jones is a stronger oxidizing agent. Like this Jones reagent uh, was able to oxidize the primary alcohol into the more oxidized state. PCC is still doing oxidation, but not as strong as Jones, right?
Oh, okay.
Uh-huh. So a primary alcohol would be converted to an aldehyde if you use PCC. A primary alcohol would be converted to carboxylic acid if you use Jones, right? So you can memorize it like that, but it's best if you understand like why that is the case. By understanding the concept between a weak and strong oxidizing agent, right?
Right. Okay. I think it kind of makes sense.
Uh-huh.
So, just to summarize, what we said was for a primary alcohol,
Mhm.
if we have it reacted with a weak conjugate base,
Oh, weak oxidizing agent.
or yeah, weak
Uh-huh.
oxidizing agent, then
Right.
it will partially oxidize as an aldehyde,
Mm-hmm. Mm-hmm.
only gaining one bond to
Mm-hmm.
oxygen.
Mm-hmm.
And then for Jones, if it's a strong oxidizing agent, we gain two bonds
Mm-hmm.
to oxygen into the more oxidized state.
Yes, yes, you got it. Uh-huh.
That
Yeah.
makes sense.
Mm-hmm. And now let's move on to secondary alcohol, which is the easier role because it doesn't matter if you use PCC or Jones. The secondary alcohol will just go to a ketone, right? If you track the green carbon here, which is that green carbon, it only has one hydrogen to give up, to lose. So if it loses one hydrogen, it gains one bond to oxygen, right? So in both states, like both reagents here, we just get the ketone. We get rid of one hydrogen, we gain one bond to oxygen, like that. We can't get a carboxylic acid here on the Jones because that would break the octet rule of that green carbon. That's not possible.
Okay, that makes sense.
Uh-huh. Now, if we look at the tertiary alcohol here, there's no hydrogen there at the green carbon. So when we oxidize something, when we gain a bond to oxygen, we have to lose a bond to hydrogen, right? So we can't oxidize this at all, giving us no reaction because there's no hydrogen to give up to gain a bond to oxygen, right? Because
Oh,
you notice how like every time we oxidize something, like we gain a bond to oxygen, we always lost the bond to hydrogen.
right, but there are no hydrogens there.
No hydrogens here, right? It's
So,
like trading a hydrogen for an oxygen.
okay, so does that mean if there's no hydrogens to give up, no matter what the oxidizing agent is, it will still have a no reaction?
Yep, that's correct. Uh-huh. And
Uh,
you might also see this in predicted product. You could oxidize an aldehyde into a carboxylic acid by using Jones. Right. So if your reactant had an aldehyde and you see Jones on the arrow, your product would be a carboxylic acid, the more oxidized form of the aldehyde. But yet we have to use a strong oxidizing agent to do that.
okay,
Uh-huh. So let me give you let's see, 1, 2, 3, 4, 5 practice ones for you to try after this office hours, and then I can check it tomorrow.
okay.
Uh-huh. Okay. And one more here. Okay, try these five practice problems. And then you can send it to me through Discord if you're finished, and then I'll check it when I have time, or if not, I'll check it in next week's office hours. But I'll probably have time to check it over the weekend or something, or tomorrow. Uh-huh.
Okay.
Yeah. Uh-huh.
Okay, thank you so much.
Yeah, no problem, Alicia. Uh-huh. See. Oh, hey, Wiley, hey, Zinyan. Let's see here. Office hours just ended, but did you guys have any questions that I can answer last minute for tonight's office hours? No, I see. That's good. That's good. Were you able to learn from this, Wiley? Like this oxidation, alcohol, acidity of alcohols for your Chem 128A class, I think. Oh, we haven't learned alcohols yet. I see. Okay. We need a review. SN2, SN1 definition of oxidation. Yeah, that's good. Yeah, which you could use these terms here for the definitions of oxidation and reduction. That's good. Yeah, so that. Oh, it was a quiz 4. See. Did you do well? I don't know. Yeah, I see. That's good. That's good. Did you finish in time? I know Levin's tests are like super fast. Okay, that's good. That's good. Yeah. We'll just wait and see. It's okay. Uh, Zunian, how did your midterm go today for 118C this morning?
It was not bad.
Yeah, I heard it was like exactly the practice ones we posted on Canvas, right? So like if you did that, then like, I think you did well.
Yeah, it was right, like exactly the same, but like except one
Uh-huh.
response.
Well, free response. Did you have to
Um,
close rings at all and make the alpha and beta enantiomer of like in-share confirmation? Like, did you have to close the ring from a Fisher projection for free response?
no.
No? Oh, that's interesting. Oh.
He asked like, what of the following products can you get from thiazonium or thioacetal? That was like the only.
Oh, thiazolone thioacetal, and that's
Yeah.
the one with chapter 23 where you make a symmetrical or asymmetrical alpha hydroxy ketone, right? Like that,
Yeah,
that reaction, the very end of chapter 23. Were you able to get that?
I think I got it. I hope
Uh-huh.
so.
Yeah, and that was a free response question. Like, was it a mechanism or was it a predictive product problem?
Synthesis, but
Oh,
like the
yeah.
synthesis came from the multiple choice.
Oh, yeah. So you just referred back to your multiple choice and you got the answers from there.
No, like from the practice.
Oh, from the
It's like
practice.
a multiple choice practice question, and he turned
Uh-huh.
it into a free response.
Yeah. That's good. So you
Okay.
definitely did better than in the second midterm, huh? Than the first
Yeah,
one.
definitely. Yeah.
Yeah, that's good. That's good. It's good to hear. Okay. Yeah. So I have a session coming up right now, but good luck with everything, guys, and I'll see you guys next week. And also in person, December 7th, Saturday, when I do final review sessions.
Okay.
Uh-huh. Yeah. See you guys. Bye. Good night. Mhm.